series of webinar that we have been continuing every 1 or 2 months. This is for pure mining engineering. But again, the aspect of mining engineering that we will cover is the geotechnical aspect. We are not going to cover the mining aspect or the design aspect. So anything that pertains to certain branch of civil engineering, that is geotechnical engineering, in the field of mining, yes, we will try to answer those queries using GTS NX. Now, so the agenda that I have set for today is that here I'm going to demonstrate the methodology of using the finite element method to make mine designs more stable and safer in an efficient manner. Because again, while designing something, we have to ensure we do not spend too much time, or we have to avoid redundancy. So today in this examples, I'm just going to show you some easy methods to get some simple answers. Then again, in the upcoming sessions, we will have more complicated methods. And again, every site is different. So an engineer has to use his or her own perspective on what degree of efficiency and what degree of safety they are looking for. Based on that, the time taken for your designs will vary. So on the left, you can see three pictures. So the top is the picture of a block model, but yes, it is not the block model from any block model developing software like Surpac or Vulkan. This is the block model that has been developed in GTS NX. So when I said developed, that doesn't mean that we can create block models in GTS. Instead, from Surpac, what you do is you have to export in a certain file format. Then you can import the entire block model into GTS. So how to do it, I'll tell you that later on. So with the uh, index that we have, I'm going to show you some basic examples of mining engineering and some design tools in GTS and some real-time application areas and previously done projects. Apart from that, the second section will have the description to numerical model. It's a very simple 3D numerical model, but it is more than accurate. And why is that? I will tell you that while I show you to the I take you to the numerical model. In the third, it is basic analysis and output of FEM results, the output tools, and the factor of safety, since it is an open pit. So we will have the factor of safety, and then the displacements and strains and the stress distribution. So starting with the introduction part. So mining engineering, it has various branches. It can be done in the open pit manner. It can be done in the underground manner. Then placer mining is there. High wall mining is there. So the definition for mining engineering, it can be applied to a multitude of tools, and this is one of the oldest professions in the planet. Since the day humans have used the metals for our own advancement of civilization, mining has been done. So a lot of you might who are working in the mining industry, you might have seen some old caverns popping up in the area where an open pit is being operated currently. For example, the Kalgoli super pit or the Rampura Agucha lead zinc open pit mine in India, they were both found to have or previously existing underground caverns. So which essentially indicates that mining was done there before, like much before we started mining in those areas on the large scale. So the top left picture that you see is that of a an open pit mine. So now the question is how to simulate the same thing in GTS. So if you have your drawings, you directly import those drawings. You do not need to redraw it again in the software. That is redundancy. So what you can do is it can be done in three ways. The first way is by the export of block model, which I'm going to show you in the next slide how to do it. Or the second is the easiest way. That is, you just have to export the triangulated surface or the digitized surface from your block model and then export that into GTS. In that way, you can have multiple files for each stage of the mine throughout the life of mine where you can assess the factor of safety. Okay. Same thing goes for the top two. If nothing else, you can always export your contour, CAD contour file in the DXF format, or you can have a point data cloud for the mine and then import that into GTS. So every method works, and then finally you will end up with this one. That is a 3D solid model inside GTS. Next, we will talk about block model development. So when you have developed or your team has developed the block model in your software like Surpac, Minex or Whittle or Desvik. So from there what you do is just export the ID, okay, the XYZ coordinates and the locations and the material. That is all you need to export, and that should be done in the CSV format. So once you have done that, we have a tool in GTS that is called as the block model converter. It converts the block model into two types, either into surfaces that can be used to cut solids or directly into mesh like this. So this is a model that I'm going to show you towards the end, but I will not show you the analysis parts. I'll just show you how it was developed. Okay. So this is a very comprehensive tool, especially for deep analysis. So if you want to have more degree of satisfaction or more degree of accuracy, then this is something you need to do. Like develop your GTS model from your block model right away. So now coming from open pit, the next part in mining that can be done is tailings dam. So some of you might have been familiar with the tailings dam incident that happened 2 days back in Jägerfonstein, that is in South Africa. So the entire embankment wall collapsed in one side and the town is flooded. So that is making right currently that is making hot rounds in LinkedIn. Unfortunately, these events happen. So somehow in the future we have to ensure that these events do not happen. So numerical model is a very good tool to approximately prognose what can happen in there. Okay, so we do have a comprehensive webinar for tailings dam. So this is an upstream tailings dam, like you can see, with 11 raisings, and then this is the starter dike, and then the buttress wall. So you can see after the seventh raising on the chart, the factor of safety drops to below 1.5, and the higher you go, the factor of safety will drop even more. So, which essentially means that the buttress wall that has been created here is going to provide an adequate support only till raising 7, like until this part. Then after that, it is all left at the mercy of nature. So these tools help us to eradicate certain issues like when do we need to start creating a buttress wall and things like that. So apart from that, you can also get the seepage data from there, the phreatic line, and then the if you want to do consolidation analysis, you can also do that. Okay. Now coming to underground mining. So one of the examples is of ore passes. So this is an ore pass for an underground metal mine. So this is an ore pass that has been created in it's a very good rock that was almost intact gabbro. So you can see the rock was so competent that even the the main haulage ways only needed some steel arches and a very thin layer of shotcrete. There's no rock bolt needed in here. So here you can look for stress concentrations, plasticity concentrations, tensile areas, highly stressed areas, or yielded zones, or zones very close to yielding, then this stress distribution will also show you that which areas will need extra support. Like in the picture on the right in this part, you can see in the main haulage level or in the main level, the stresses are very much concentrated towards the end of the wall. So on the long run, it might be problematic, okay? But since it is an FE model and the model converged, that means as of now the wall is safe. But until how long the wall is safe, for that we need to do a creep analysis or a parametric analysis or a probability analysis. Okay. Second part of the underground agenda is the presence of a fault zone in an underground metalliferous mine. So this fault zone actually crisscrosses the crosscuts. So here you can see this is the main haulage main uh, haulage level. From there, you have the crosscuts going to the ore area, and the main haulage. This part is a very competent rock. So this was only supported using steel arches and some thin amount of short grid, but we did not model the short grid because we wanted to check for stress concentrations. And then the crosscuts. As the fault zone was crisscrossing the crosscuts, like you can see here, and we know for a fact that this will be the weak zone. So these areas help us define that what extra support is needed nearby, because stress will always travel from a weaker zone to a stronger zone. That is why along the transition zone, which is exactly this, you will have to provide extra supports. So people among you who have been to deep underground mines, they will be able to see this effect right through the eyes. I have also experienced and seen these things, like when the stresses along the transition zone became so high that the rock bolts completely yielded, and then the shotcrete and the wire mesh was completely folded. So these do happen in deep underground mines. So I hope everyone is clear with the application areas of GTS NX. Next, we'll go to the numerical model description. As I mentioned, it is a very simple model, so there is not much to ponder about it. But along the software demo, I'll show you some of the other tools. So at first we'll start with the workflow process. Some of you might be new to numerical modeling. So in the workflow process, you have to first start with the geometry. Either you can create your geometry ground up, but I will recommend if you have the CAD file from your drafting team, just import that. There is no need to develop a geometry ground up that has already been developed in a different software. Then second will be the material property definition. See, this is where a lot of people create mistakes. To be very honest with all of you, when I was very new, I have also done some mistakes with material properties calibration. So no matter what software you use, your material properties should be thoroughly calibrated. You can have certain aspects of difference in geometry, because again no one expects you to replicate the exact like geometry or the topography 100%. It is very hard to achieve that. So what you can exactly do is you have to replicate the material. The material should be as close to reality as possible. So that is something we have to take care of often. Then the element attribute. So after your geometry, material and the element attribute has been defined, you have to create the mesh. Then the loading and the boundary conditions. For open pits, we just take the gravity loading. For undergrounds, we take the gravity loading or the body force as well as the pre-existing stresses. Because in deep mines, the horizontal stresses the horizontal stresses are much higher than the vertical stresses. So that is something we also need to take into account. And based on that, that the flow of the horizontal stress path is what defines the orientation of the crosscuts and the main tunnels. Otherwise, if your main haulage road or your main tunnel or your main sublevel, these are perpendicular to the principal stress, then yes, you will expect major damages throughout the lifetime. Or in other words, you can always expect a wall failure to happen. That is why tunnels or haulage roads, everything that is deep underground, they are designed in a way that they are longitudinal to the major principal stress that is in the in situ ground. Okay. Then we define the boundary conditions. Finally, we create the analysis case, and in the end, since this is a graphical user output, so you'll have a contour map, you can have the probe options that you can pick any node and see for the results and the report. So next I'll show you the import file for GTS. So on the left you have the SURPAC file. A lot of you might have seen this kind of services from SURPAC or your mine planning software. So all you need to do, just export that surface, okay, and in DXF or DWG format. Then this is how this is being imported. So some people who haven't seen these kind of surfaces, I'll let you know that this is what is called as digitization and triangulation. That is why you can see the strings are connected. So these strings are what GTS takes out of these surfaces, and then it automatically assigns the nodes when we mesh it. Okay. So after that, this is how the model will look like. Now, so the question that comes to the head is that what exactly is this kind of mesh? So in GTS, you have two kinds of mesh. That is the tetrahedral element and the hexahedral element. Both kinds of elements are present in here. So with the hexahedral element, you get a few more nodes. But the best part is that it has more since it takes more area and has more nodes. The total number of nodal count in using hexahedral element will be lower than using tetrahedral elements. Okay. Next, the boundary conditions. So in GTS, you can have the basic boundary conditions if you want to define them manually, or the advanced boundary conditions. And then we have the auto boundary conditions. So if your model boundaries are orthogonal like this, then just use the auto boundary condition. So in an finite element software, you have to remember the boundaries should always be orthogonal. If they're not orthogonal, you have to manually define the reaction at each node. So it is easier to have orthogonal boundaries than manually defining nodes for your manually defining the reaction direction for your nodes. Okay. So we have covered the introduction part and the numerical model description. So now finally coming to the output. So the factor of safety of this particular model is, or this particular open pit mine is 1.85 or 1.9, and this is the critical area. So this method uses the SRM methodology. So SRM is nothing but the shear strength reduction methodology. So what is that? I'll tell you in the numerical model. So these are the principal stresses. So now finally we will go to the numerical model. So any questions till now for us, or should we directly jump into the model? If you have any questions, please feel free to ask us. I'll try to answer that to the best of my abilities. So if there is no question, then we'll just proceed with the model. So this is your surface. So you can see this is the main pit, okay, and this is an auxiliary pit in the end to ensure maximum recovery rate. And this is actually very common in big mines. So what to do next in here? It is actually quite simple. We just create the solid and cut the solid through. So what I'm gonna do is I'm gonna activate the grid. Okay, I'm gonna activate the axis. I'm gonna change the orientation of the grid to the vertical plane. I'll go to move work plane. Click here, press OK, and you can see the grid orientation has changed. I'll go to top view. So this is my pit. Here. Now what we do is just create a solid to cut through this particular faces. So I'll go and first go to create a rectangle like this. Okay, I'll hide the grid. So for this rectangle, I'll just translate that to a lower level in the z-axis. So I'll use the translate option, select direction, z-axis. Let's say the distance is minus 200 because we are going in the negative z direction. So this is good enough for us. So I'll press apply. Now all I need to do is I'll just extrude that in the vertical direction. So I'll go to protrude, extrude. Target face is this. Direction is z-axis. Okay. Let's say my length is 500 meters. Is it good enough or not? We'll see. Yeah, that's pretty good enough. So we'll press OK. So there you have it, your solid and the particular face. So now what we do is, it's quite simple from now on. Let's go to the divide option. Click on solid divide, my target solid, my tool surface. So I'm just gonna hide the solid, select the tool surfaces, press. So what happens now is that after that, what happens is that our solid has been divided, and finally we generate our final solid, that is this one. Okay. So here, after our solid is created, one can say that we need to create our borehole logging data. So for that, what we do is just go to bedding plane wizard, So if you have a log data in Excel, you can actually import that. Otherwise, you can just, let's say my name is BB1 or borehole 1. Okay, so let's say B1. I name it as 1. So for location, let's say I give the location as for the first borehole as, let's say, in this part. Okay, so here I just need to define the depth of each layer. Let's say my first layer is 20 meters, second is 30 meters, so that will be 50 meters. Third is, let's say, 50 meters. Let's say third is 100 meters. Fourth is 300 meters. I press modify. Now what we do is this second one. Let's say my second borehole is somewhere around here. Okay, the depth is, let's say, 35 meters for the first layer. Second is 75. Third is, let's say, 250. Fourth is 400. Okay, then my third borehole. So please remember that whenever you import or put borehole data in here, you need to have at least 4 boreholes. So in that way, the clarity becomes far better. So I put the, let's say, the location in here. My first layer depth is 49 meters. Second is 90. Third is 275. Fourth is, let's say, 400. So let's see now how our boreholes look like. So for the elongation of planes, I'll put that in the x-axis as 100 and y as 100. I'll press review. Can you see? It seems 100 is not enough, so let's say put it as 500 and 500. Press OK. So these are our major boreholes. So you can see that is how you can create your borehole stratigraphy in here. So let's say I want to cut the solid using the borehole data. You can actually do that too. So what you do is just go to solid divide, press this one, select the tool surfaces that you want to cut the solid with, okay, and then press OK, and then they will be done easily. Okay, so it is quite simple to get these things done in GTS. So one need not need to worry about it. Okay, now I'll just hide the borehole logs. I'll stick to the basic model that we have. So next we come to the material property definition. So we have used only one rock type because again the we didn't want any complications for the introductory session. So I just named it as a rock. So we have given that the property of very close to igneous domains like let's say the biotitanate or almost let's say intact granite. So this is around 3.5 GPa of E modulus, Poisson's ratio 0.3, the dry unit weight of 27, saturated unit weight of 28, position 150, friction angle 45 degrees. Something you have to remember is that for more coulomb, there are 5 inputs: the E, nu, gamma, C, and 5 Le. So this particular FEM slope stability method, it is only applicable to more coulomb modified Moore column, hardening soil, and generalized Hook-and-Brown. For rocks, we use Moore column and generalized Hook-and-Brown for the input properties. So uh, both will support the SRM method in here. So here we have the different metal properties that you want. For rock mechanics, you have Moore column, generalized Hook-and-Brown, Hook-Brown. We also have this CWFS, that is the cohesion weakening friction strengthening material. Okay, and then the rest are mostly for soils. So if you are working in a tailings project and you want to check for the liquefaction, you can have the modified UBC sand or PM for sand or NOR sand material. Now, so the methodology that is employed by the software to create uh, the factor of safety analysis is the SRM or the strength reduction method. So it is nothing but the shear strength of the material is reduced. So here you can see the cohesion value is 150 and the friction and angle value is 45. So using the Moore Coulomb theory, we can calculate the stiffness or the shear strength of the material. So what the software does is that it gradually reduces the strength of the material by a predefined factor. So that predefined factor is normally 0.1 that is taken up by the software. It can be low, you can set it to a lower value like 0.5 or 0.05. So it can be lowered and raised to. So now the question is that why would you do that or change with the software properties? The thing is, if you have a very competent rock body, then yes, you can always increase the tolerance criteria. But otherwise, for soils and for fractured, fragmented, or weathered rock, it is better not to tamper with it. So, if you all remember the PPT that we had, the factor of safety was 1.9. So 1.9 factor of safety is nothing but it is this particular the C value divided by 1.9 and the friction angle is around tan inverse 45 divided by 1.9. That will be your friction angle at failure. So if we just calculate that, so at failure, so if I just go to 150 divided by 1.9, so if somehow or due to natural calamity or due to some external forces the cohesion value drops to around 80 or 90, then this slope will collapse. Same thing goes for the friction angle too. So the calculation methodology is quite simple, that the software reduces the shear strength values until the failure surface is reached. So now we'll go and mesh it. So I said there are two types of meshes. So one was the hybrid mesh and second was the uh, and the second was the tetrahedral mesh. So I just go to 3D. Okay, select this. Let's say this size around 35 meters. Select the hybrid mesh. I'll try to put on higher order element as much as possible, and we'll see the nodal variation. So 30 meter looks good enough for us. Okay, like this. This is how your nodal locations will look like. Name it as pit trial. Press OK. So it will take a couple of seconds to mesh the model because it is a very big model size. So it takes a couple of seconds to mesh it. So any questions till now, please feel free to ask, or any doubts that you want me to take care of. So we will see. Again, anyone, any questions? So I have a question from Mr. Shovan that while incorporating SRM method, how does the factor of 1.9 comes up? See, when we employ the SRM method, the software does all the iterations. It's an iterative method. So the software reduces the factor of the C5 value and reduces the shear strength by a predefined margin, that was 0.1. So the calculations will start from 1 until it will go to a factor where the model will reach divergence. So at the stiffness value, when the model reaches divergence, that is when the software will calculate the shear stiffness at that particular moment just before failure with the original parameters that we had set for the material. That ratio becomes the factor of safety for that particular model. So there is one more thing that you have to remember, that the values that you get from the SRM analysis are the values just before failure. Okay, because the model has diverged after that particular iteration. So whatever iteration results you are getting, that will be the moment after which failure will happen. Okay. That is why the values look bit higher and exaggerated. So a lot of people have doubts that the values that we are getting are very high from the slope stability analysis. The values will be high because at those threshold values the slope will fail. So that value will be high because the slope will not fail at a lower displacement value or a lower stress value. So that is something you have to take a look at. So after the meshing is done, we just go to define the boundary condition. Okay. So we'll go to static slope analysis, go to constraints. We'll click on auto constraints. You can see roller supports on the sides and fixed on the bottom. Then we'll go for the loading condition, that is the gravity loading. So I name it as SW11. Press OK. Now after this is done, I'll go and define my analysis case. So I had always put on stress today that we have to ensure that our material calibration is correct. So how do you know your material calibration is correct? That is, you have to try at first. Do not directly jump into a construction stage model or an SRM analysis in the very first attempt. Chances are you might be wrong with your parameter calibration. That is why you have to do a linear static at first and then a non-linear static, because these two will show you whatever faults are there in the calculation methods. So our target is to check that if the calibration is proper and correct, these results should match each other. It doesn't matter. Just because in a linear static the material there will be no the material will behave elastically doesn't mean that the stresses become infinite. They will be limited to one particular area only. So that is something we'll try to see in the results now. So I have run this model for you. Now we're going to check the results for. So I'll start with the non-linear static first. So the displacements. So please take a closer look at the displacements. The total displacement is around 10 point, at max is 10.37 centimeters. Okay. If we activate the vectors, you can see this look like this. Then the horizontal displacements and then the y direction displacements. So now you know from this chart or from these results, if you in case want to install a pit monitoring radar, what threshold values to look for from time to time. This is what you get from numerical results. And these vectors and these displacement values in each direction, they indicate what kind of displacements to expect from which area, and at the same time what should be the threshold. So we are in the linear static zone right now. The Ty value is 0.67 or the y direction displacement. Okay, this is the y direction, the x direction, the z direction. The x displacement is 0.35 and the vertical is 10 minus 10.37. So vertical minus 10 means there is settlement in there. Similarly, we'll go to check for stresses. The minor principal stress, that is looks like this: 1719.91 kPa to minus 6571. The major principal stress 48 kPa to minus 15,000 kPa. Okay, like this. And the stress paths like this. So after the linear static, we'll go to the non-linear static. So if these values match for both the analysis, then our model and the material properties both are correct. So we'll start with the total displacements. The value is 10.37. If I again show the value from linear static, it is 10.37. Okay, our first thing matched. Then the Tx, it is the same 0.35. Then Ty 0.66 to 0.93 is exactly the same, just a bit higher, 0.01 centimeter higher. So that is like virtually nothing, or 1 mm higher. Okay. Then the stresses for the non-linear part, the minor principal stress, and the major principal stress. So the major principal stress was in the linear static, it was plus 49 to minus 15339. In the non-linear static, we have plus 74 to minus 15339. So it is very, very close. So this is a good way of assessing if your calibration has been done correctly or not. You can add multiple materials in there. Let's say this entire pit is made of 30 different type of materials, but these values, they should be very close to each other. It doesn't matter. Okay. Then we look for some plasticity status. So you can see the yield zones around the mine. But again, the model has converged. So we cannot say this is exactly yield zone. This might be very close to failure, but it hasn't failed. If your finite element model fails, then you can say that yes, there are yield zones, and you'll get plasticity, concentrated at one particular area. Then the strains, the shear strengths. So these concentration of shear strains are one of the indicators that this is the area that will be the most critical while doing the slope stability analysis. Okay, then the plastic strains, same. So now, if we go to check for slope stability results, the factor of safety was 1.85. If you can see the total displacements, that area in the non-linear static that showed the maximum concentration of the plastic and shear strains, that is what is the critical area in here. So remember when I said that the results for SRM you will get is just before failure. So you can see the displacements now, 42 centimeters. So this area will pop up 42 centimeters and then it will completely diverge. Okay. Then the horizontal transformations like this. So if you're looking for a massive bench failure on this area, you know very well what values will induce the bench failure there. Okay. So a 9 centimeter movement in the x direction from these areas will induce bench failure. Okay. And the TY movement, that is around 40 centimeters. So this area needs to move inwards in 40 centimeter to again induce the bench failures. Since this is a 3D model, the results you are getting will be on the 3D format. But do remember, in an actual site conditions, the bench or the particular high wall might fail if any one of the three criteria have been met. That is why we put very stringent threshold values for high wall monitoring. Okay, and then the shear strengths here, your most critical region, volumetric strain, the same. So again, your critical region should never move. That is also something you need to remember, that your critical region of straining should never move. Then the plastic strains. And finally, the factor of safety of 1.85. So for today's session, that is all I had to show to all of you. If you have any questions, please feel free to ask now. So I remember telling you that I'll show you a model developed from block model conversion. So this is the model that you will develop by your block model conversion. Okay, like this. You can see these are all blocks. So based on your open pit scenario, they can always be cut down. Due to NDA agreement, we cannot exactly show you how it looks like. So all I can show is how the block model once converted will look like. So any questions till now, please feel free to ask. The overpass model. Then for underground pillar design, you can look at the stress concentration along the pillars. So I have a question from Mr. Shobhan that do we have any insight on how does the FOS of this 3D analysis compares with simplified plane strain and slope stability analysis with the exact same properties? So yes, we do have a lot of studies because again that is a part of my job to compare 3D and 2D analysis. See, to be very honest with you, for some models, simplified 2D analysis is good enough. Then for some model, you need 3D modeling. Example, this particular one. The exact same model that I showed you. Because a 2D plane strain analysis means if I just go for the side view, if I let's say you have this tool called as clipping plane, it's gonna look like this. So if I go to the side view, so in a 2D plane strain analysis, this is all you will have, the bench. Okay. And the assumption is what? That this particular bench is ranging to infinity in the longitudinal direction. But here this is not the case. So in these models, the whole necessity for combining a 3D model is that we are looking for a full global factor of safety analysis. For a local factor of safety analysis, yes, you need a 2D model. Do not go for a 3D model in simple local slope stability analysis. So when it's a local slope stability analysis, it means let's say I want to check out one section of the mine. We just cut it down like this particular part, then yeah, that is enough for me because I am only checking for that particular section. But again, for me as a mine operator or a mine regulator, it is also part of my job to understand how big will be the entire sphere of influence or how big of an area that I need to monitor. So that is why we need to do a plane strain analysis for only local modeling. But for a global modeling for a pit like this, yes, you need a 3D analysis. So any further questions from any of the participants, will be happy to answer that. So if you have any questions for mining activities or geotechnical questions, please feel free to ask us. Or even if you have any generic question about the uses of the software, please again feel free to ask us. So I have a question from Mr. Gregor that is it possible to import CSV data? So Mr. Gregor, you need to elaborate what the data from CSV you want to import. See, CSV data can be imported into your block model from where you will develop your comprehensive model like this. Otherwise, there is no point importing that much amount of data into GTS because again, analysis software is not built to handle that big range of data inputs. So you can also develop your faces from using the point cloud data. So we have this option called as point face. I'll share my screen with all of you right now. Okay. So if you can see the screen in the geometric part, if I go to create face, we have the option where you can import point cloud data. You can directly import your coordinates from Excel. Okay, like the input table. You can you can copy paste them, or you can always import your points. Okay, the imported file format supported are text formats and Excel formats. Otherwise, copy paste will also work. Otherwise, if you have your DEM data, that is digital elevation model data, you can copy paste them right away in here. I'll just show you an example of DEM data. It looks like this. So you can directly copy paste the data and you will have a complex face developed over there. Okay. Any further questions? So I have one more question from Mr. Pritham. Is it possible to determine the ultimate final pit slope uh, with the factor of safety value? Like while designing our benches, we can plan accordingly as per the FOS slope. Mr. Pritham, you need to understand, remember this, that your bench local slope angle. So when I say local slope angle, that means the angle created between two adjacent benches. It can be varied and it normally varies in every mine based on the stiffness of rock at that point. That is why you can see even in this particular mine, this face is concave shaped. Some faces are convex shaped too, depending on the rock stiffness on that particular area. But if you watch closely, the ultimate pit angle at each point from the toe till the top is constant. So that is something that has to be maintained. Your ultimate pit slope angle will be constant, but your local pit slope angle is variable depending on the progression of the mining. And again, the final pit slope angle can be determined obviously with the FOS value. Yes, because again your FOS will determine how you want to proceed with the mining. Here the life of mine or the LOM, it extends according to how you have planned your excavations, at the same time how you have designed the benches. So both of these should go hand in hand, otherwise you might lose on your extraction point, that is on the economical aspect, or you might lose on the safety point, that is your, you can get a slope failure if you have designed your slopes to be too much let's say too much vertical. Okay, the final bench slope angle, Mr. Pritham, yes, it can be easily done in this. And actually for the fun part is that for final pit slope angle, do not directly jump with a big model like this. Always start with a small 2D plane straight model. See, for every model, you do not need a perfectly modeled 3D analysis. For some questions, like for the final pit slope angle, or the final angle of dump, or the final angle of the stockpile, that is something you can directly get out of the 2D plane straight model. You may not need something like this. Okay, clear? Any other questions? Please don't hesitate to ask any doubt you have, because it will also help us create future content. So please feel free to ask questions wholeheartedly.